just a little bit about the OECD UNEP Global PFC group for those of you who are not aware of the group. So this is a group that came together to help support the SICEM mandate of shifting to safer alternatives to PFASs and to share information on risk reduction approaches. Things that we have as part of the group is a webinar series to share different information on alternatives and risk reduction approaches. Just before we get into today's webinar, I'll just also like to mention that we're looking to schedule another webinar in December on best environmental practices related to firefighting foam. So please look for a notification for that coming up, but we're still settling on a date. And certainly if you have other suggestions of webinars that the group should hold, or some work that you're doing that you'd like to share with others, please don't hesitate to contact myself, Eeva Leinala, or my colleague, Marie-Ange Baucher at the OECD. So today we're grateful to welcome some representatives of the MIDWOR-LIFE project. So this project looked to mitigate environmental health and safety impacts from durable water and oil repellents. And we'll have in this webinar 4 different presentations, about 10 minutes each, regarding different aspects of the project. And then I'd like to go through all those presentations. So you'll also just like to thank Marie-Ange Baucher for organization of this webinar, and also Laura Dawkins that's helping us on with the webinar, the WebEx itself. But at this point, I'd like to turn things over to Ruth Garcia, who will talk about the project objectives, methodology, and technical results of the MIDWOR-LIFE project. So please, Ruth, go ahead.
Okay, thank you, Eva. My name is Ruth Garcia. I work at LEITAT Technological Center, and I have been responsible for the assessment of the technical performance of the different viewers studied in the MIDWOR project. I'm going to present the project objectives, the methodology, and the technical results. First of all, during all the presentation, we'll be talking about DWOR. That means durable water and oil repellents, and it refers to the chemical products used in the textile finishing industry to oil repellency to the fabrics. The conventional DWORs used in the textile industry are based on long-chain fluorocarbons, or C8. From the environmental perspective, the main concern raised by these DWORs is that its fluorinated may be severed from the polymeric backbone, releasing perfluoroalkyl substances, or PFAs. Later, these PFAs will degrade to form highly persistent perfluoroalkyl acids, or PFAAs, and among these acids, the most concerning are perfluorooctanoic acid, or PFOA, and PFOS. PFOA is already listed as a substance of very high concern and will be restricted from June 2020. And PFOS has been included under the Annex V of the Stockholm Convention as one of the substances that also the European Union has limited the presence of PFOS in consumer products to less than 1 microgram per square meter in coated products. The perfluorinated substances can be released during the whole life of the textile products and are very persistent and bioaccumulative. Thus, they represent a high risk to both the ecosystem and humans. During the MIDWOR, it has been studied how to mitigate the environmental impact of DWORs by using non-toxic alternatives. Regarding the objectives of the project, it is included the evaluation of the environmental impact, the risk, of the current DWORs and their alternatives. The global aim is to reduce the emission and exposition to toxic compounds derived from the use of DWORs. Okay, and starting with the project itself, this is the outline. During the preliminary actions, a technical screening of the different DWOR technologies was done, and the environmental considerations were taken into account in order to do a selection of the 14 DWORs that have been later applied. 5 fabrics were also selected, and the pre-industrial application tests were done at LEITAT facilities. Some of the products were then applied on 6 different textile manufacturing companies in order to confirm these results at industrial scale. During the industrial applications, some data was gathered for the next steps, which are the risk assessment, the life cycle analysis, and the technical assessment. Finally, during the whole project, workshops and communication actions have been done in order to and make policy recommendations. In this slide, you can see the fabric selection, where 5 different sectors are represented. The automotive sector with a polyester non-woven fabric, the sport and work sectors, which have the same knitted polyester fabric, fashion with a woven woolen fabric, and upholstery with a woven polyester fabric. Regarding the finishing product selection, it can be divided into 2 main groups. First of all, fluorinated DWORs. In this category, long-chain fluorocarbons, or C8, short-chain fluorocarbons, or C6, fluorinated silicones, which are in short-chain carbons, but incorporate the silicon chemistry, which provides a softer feel to the hand. The second group, non-fluorinated alternatives, which are silicones, dendrimers, or hyperbranched polymers, paraffins, or linear aliphatic hydrocarbons, and finally, alkyl urethanes. These products have been applied by petting, first on laboratory scale, selected to be applied also on an industrial scale. These are the 6 textile manufacturing companies that have been involved in the project during the industrial demonstration. Each company has treated 1 fabric using different DWORs. Notex and Nanomembrane from Czech Republic, being responsible for the automotive and upholstery fabric, respectively. Agio 2000 and Via la Manifatture Tessili from Italy have been both responsible for the wool fashion fabric. And finally, Hydrocolor and Encima from Spain have been responsible for the work and sportswear fabric, which is the same knitted polyester fabric. During the industrial demonstration, the selected products were applied onto the fabrics, adapting the parameters used in the lab to an industrial scale, but always maintaining the same product concentration used in the laboratory trials. Questionnaires were filled by the companies in order to gather data for the hazard exposure parameters, life cycle assessment, and environmental impact. The fabrics treated were then characterized at LEITAT in order to validate the technical results. This characterization is based mainly into standards, which is the water repellents or spray test that measures the resistance of fabrics to wetting by water, and the oil repellents or oil test that measures the resistance of fabrics to different test liquids. Moreover, aging tests have been done in order to determine the washing fastness of the treatments. This includes domestic washing for polyester, dry cleaning, and ironing in order to check if the repellent properties were restored with temperature. And finally, in this table, you can see a summary of the technical results obtained in this project. The water repellency grade can be from 0 to 5, being 5 the highest water repellency. In the case of oil, the grade can be from 0 to 8, being 8 the most repellent. And these results, except for the automotive polyester non-woven, which has not been washed, are from the washed or dry cleaned samples, and also ironed. In bold are highlighted the results from the industrial demonstration. And you can see in green the products that have achieved a grade 3 or higher after washing. In yellow, those which achieve grade. Finally, in red, the products with grade 0 that means that are not repellent after washing. The first table shows the water repellency, and it can be seen how some alternatives can substitute the fluorinated chemistries if only water repellency is required. Especially the dendrimer can be a potential substitute which achieves the same repellency grade than the C8 in the knitted polyester fabric. It should have been interesting to apply this product on the other polyester fabrics during the industrial demonstrations, since the results obtained are more reliable and tend to be higher than those from the lab trials. Regarding the oil repellency, it can be seen how none of the fluorine-free products has achieved oil repellency, and regarding the perfluorinated substances, the short-chain fluorinated alternatives can substitute long-chain fluorocarbons with very similar performance. Perfluorosilicons have an extra advantage since they give a softer handle, and it is needed to do case-by-case studies in order to see if oil repellency is truly needed, or we can just have water repellency and use fluorine-free alternatives. As it can be seen, the wool fabric achieved in general a low washing fastness, and the results are quite low for this fabric. And for my part, this is all from a technical point of view, and now my colleague Julio will present the environmental impact.
Thank you very much, Ruth.
Okay, good afternoon, everyone. My name is Julio Fierro, and I'm working in CETIM Tecnológical Center. And we were responsible of the environmental impact assessment of the different products that were tested in the project.
Just sorry, Julio, can I just ask you to make your slides like full screen? Yeah,
I forgot.
Then it's easier for people to see.
Yeah.
Thank you. Perfect.
Okay. Sorry. Well, for those of you that are not familiar with what is a life cycle assessment, life cycle assessment is a technique to evaluate the environmental impact associated to different stages of a process or a product, from what is called cradle to grave. So we can study from the raw matter extraction through all the processing stages of the manufacturing process, and at the end of the use and the final disposal. This kind of studies requires the collection of quite a lot of data from different sources, and then we have to model the process and in order to obtain this environmental impact calculation. In order to unify the procedures and to ensure the quality of this type of studies, there are a couple of ISO standards and also a handbook guide from the Joint Research Center that we commonly use and we use in this project. And also we use a specific support software called CIMAPRO 8. So without going into too many details, a life cycle study has 4 main stages. The first one is the definition of the scope and the objective that you want to address with the study. Then it's necessary to build what is called an inventory, life cycle inventory, which includes all the inputs and outputs of the process that you want to study of the product. This is usually the most time-demanding tasks and the more complicated one. Then with this, when we got all this data, we have to calculate the environmental impact. That it's done with a specific methodology, and after that we obtain the data, the results that then we have to evaluate. And life cycle is an iterative process that you usually want to need to evaluate the results and then go again to the inventory to improve some of the parts and so on. So it's not a straightforward process usually. So in this project, the objective of this task was to study and quantify the environmental impact of 6 different tools used by the textile industry, 3 fluorinated and 3 fluorine-free. The 6 products that we used were C8, C6, perfluorosilicon, silicon, dendrimer, and paraffin. And the results that we used for this study were obtained basically from the industrial validation process that Ruth explained before. In order to focus the study in the finishing process, we choose what is called a gate-to-gate approach. We were focused on the finishing process. For example, the fiber production, the fabric production were out of the scope of the life cycle, and also the use or disposal of the fabric was also not included in the study. So this slide shows the flow chart of the process that we studied. As I said before, we focus regarding the textile process. We focus only on the finishing process, but we included all the stages from the to our production, from the finishing, the synthesis of this product, its application, and the disposal of the waste if they were irrelevant. And the functional unit, the unit of reference for all the study, was the production of 100 square meters of finished fabric. In order to build the life cycle inventory, we use primary data from the industrial validation. Also, we use the door composition obtained from the safety data sheets and some other documentation supplied by the distributors or manufacturers. And also, we use some data from scientific papers and technical documents. We use the method used for the impact assessment was ELCD 2011, which is a method developed by the European Platform of Life Cycle Assessment. And it includes 16 impact categories that covers a wide range of fields: atmosphere, water, soil, human health, and so on. In fact, it's a combination of different global asset methods for life cycle assessment. In this development of the life cycle assessment, we find out that any of these methods at present includes perfluorinated substance in the substance inventory. Thus, at present, impact linked to the release of this substance is not taken account properly in the life cycle assessment. So we included 6 new substances, and we included into the method based on different bibliography related with this. So these are the first results that I will show you briefly. These are a comparison of the production of 1 kilogram of each door. We can observe that there are a higher impact of the fluorine-based boards. The C8-based door has the highest one, then the C6 and the perfluorosilicon fluorine-free dwarfs presented much lower overall footprint, up to 30 or 40 times lower than the C8 base. And regarding the fluorine-free alternatives, the Dreamer and paraffin presented at slightly lower impact than silicone. And regarding the textile process, we can also observe a high. This chart shows the total impact of each scenario of the 100 square meters of dwarf finishing, and each color represents one stage of the process. The orange one shows the contribution of the dwarf. The yellow one is some sort of wetting agents or other products, and the blue ones are the two stages of the finishing process, the padding and the drying and curing. So you can see there's a high contribution of the dwarf production in the fluor-based finishing. And also, it's remarkable that the perfluorosilicon presented a higher amount, a higher environmental impact than the C6. In contrast, I showed you before when we were studying only the products, just because the higher amount used in the validation. And also, as we see in the dwarfs, the environmental impact of the finishing process in the fluor-free alternatives was lower, between 4 and 10 times lower than the C8 scenario. And if we check the results by the different impact categories of the life cycle study, the human toxicity is the main category impacted by the finishing process. And also ozone depletion is highly affected by the fluor-based scenarios. These two categories accounts for nearly 90% of the total impact in the fluorine-based scenarios, and only between 60 and 65 in the fluor-free finishing. So the main conclusions that we obtained from this life cycle study is that fluorinated dwarfs production presents a clearly higher environmental impact compared with the fluor-free alternatives, that it's reflected in the textile application. The release of the tetrafluoroethylene and fluorinated substance like PFOA and PFXA are the main cause of the impact observed. Human toxicity and ozone depletion are the main environmental categories affected by this process. Also, that despite the C6 dwarf showed a higher impact than perfluorosilicon, its application in the fabric finishing was slightly lower due to the lower amount of dwarf required. It reflects that the technical performance of the dwarf can be very important, can be determinant for identifying the best available alternatives from the environmental perspective. And also that under similar conditions, textile finishing with fluor-free dwarfs can achieve a reduction of finishing footprint between 4 and 10 times compared with the C8 base scenario. And that's all.
Thank you very much, Julio, for giving us the results of the environmental impact and how the different substances result in or can be identified through the life cycle analysis to impact different attributes in different ways and some of the potential trade-offs. So we'll move things now to the next speaker, Gemma Janer, who will talk about the occupational risk assessment aspect of the project.
Hello everyone, I'm Gemma and I also work at LEITAT Technological Center, and I'll be talking about the occupational risk assessment that we did for these different DWOR alternatives. So our goal was to compare the occupational health risk associated to each of the conventional and alternative DWORs considered in the MIDWOR-LIFE project. And the steps that we follow for this evaluation were first the identification of the chemical identity of each of the DWOR active ingredients in the commercial formulations that had been considered. And here I would just like to highlight that the commercial products contain other substances that may be more harmful than the DWOR active ingredient. But since we were aiming at comparing different active ingredients, it was our intentional choice to disregard other chemicals present in the commercial formulations. So the next step was the compilation of hazard data available for the substances identified as active DWOR ingredients. And then the compilation of the operational conditions and risk mitigation measures in place in each of the industrial settings for the most relevant exposure scenarios. And finally, we use this information to compare the occupational health risk associated to each of the DWOR alternatives by means of a control banding tool, and in this project we use Stoffer Manager. So regarding the identification of the DWOR active ingredients, we had several challenges. First, just to remind that there is no legal obligation to disclose the chemical identity of a substance in a formulation when the substance does not lead to the hazardous classification of the mixture. So this means that in commercial formulations, if the DWOR ingredient is not driving the classification of the mixture, there is no need to report on the chemical identity or concentration in such formulation. So we had these situations for several of the commercial formulations, and we had to combine different strategies to identify which were the most likely DWOR active ingredients in each of them. And this was looking at in addition to the safety data sheet, we're looking also the technical data sheets and contacting the manufacturers, and also bibliographic searches on the most common chemistry of DWOR agents within a chemical family that were most frequently used in the textile sector. So this table summarizes the information. In the right column, you see the different DWOR active ingredients that have already been presented by my colleagues. And just to mention that at the beginning of the project, the C6 based polymers, which are actually 3 of the formulations that were included, and also the fluorosilicon is a C6 related compound. All these were considered by industry as a first line alternative to the C8 based polymers. This situation has evolved due to regulatory advances also during the timeline of the project. But all these are fluoro-based until the row number 5. These are fluoro-based alternatives. 6, 7, and 8 are not fluoro-based. In the second and third column of the table, you see the information from the safety data sheet, and you see the information on the chemical composition. In most cases, it's very unspecific information on the composition, but in all cases, this was in accordance and compliant with legal requirements. So something that can be extracted from this table is also that most of the DWOR active ingredients were polymers, and here we faced another challenge, and is that polymers are exempt from registration under the REACH regulation. And this is because polymers have high molecular weights that limits bioavailability, and therefore they are not considered. There is not a big concern for hazard. But we also know that there can be monomers and oligomers in the polymers, and also as impurities, but also there can be degradation products into such monomers, and then it is these are the drivers, some of the drivers of the hazard profile of the polymers. But this information is hard to retrieve given the actual regulatory context. So, but altogether we focus our hazard assessment on the monomers of the DWAR active ingredients. So this table summarizes the actual substances for which we retrieve hazard information. So these are the perfluoroalkyl kill substances related to the C8 and C6 polymers. So the perfluorooctanoic acid, sulfonate, the hexanoic acid, and hexane sulfonic acid as well. The polydimethyl siloxane, in the case of the silicone, was considered the most likely substance that had been used in that formulation. Then the dendrimer, that in this case, that was the substance was identified in the safety data sheet, and wax paraffin. So once they were identified, we compile the hazard data. We look at the hazard classification and the CLP inventory, and then also we compile occupational exposure limits in the cases that they were available. And we also look at toxicological and ecotoxicological studies from the literature, and we checked also on the basis of those studies if the data was consistent with the CLP hazard classification. And then once we checked that all these information sources were consistent, we decided to base our assessment based on the CLP hazard classification, on the most common notifications in cases that there was no harmonized classification. And just one note that I'd like to make now is that there is generally less data on the toxicological properties on ingredients of alternative DWAR technologies, just because most scientific research has focused on the conventional polyfluorinated substances. So this may lead to a situation that conventional substances hold hazard classifications that are just due to the fact that more data is available for them. That doesn't mean that alternatives may not have such hazard classification if data would be available. This table summarizes the information on the hazard classification, and you can see that the C8 substances hold several hazard classifications. They have harmonized classifications, and they are considered carcinogenic, possible carcinogenic, and toxic to reproduction. So these are considered CMR substances. In the case of the hexanoic acid, this only classified as skin corrosive, and for the sulfonic acid, there are no notified classifications for hazard, although it's in the candidate list for substance of very high concern due to read across with the C8 homologs. Then in the case of the PDMS, the majority of the notifications do not classify this substance. The dendrimer was a skin irritant and eye irritant, and the wax paraffin is not classified in the majority of the classifications. If we just move to the exposure part, in addition to collecting the hazard information, as I explained, we also collected exposure determinants in each of the relevant occupational exposure scenarios with the goal to derive exposure bands for each of them. So first, we used the lab pilot scale trials that were performed at LEITAT to identify the key exposure scenarios. And then we went to the industrial demonstrations to actually look at each of these. And in some cases at the industrial level, some of these exposure scenarios were not considered relevant, were no longer considered relevant due to the fact that they were performing in closed conditions. And then the ones that continued to be relevant key exposure scenarios were the formulation step and the padding application by itself. So this slide summarizes the outcome of the exposure assessment. For this assessment, we had to use a concentration value for the substance in the product. We use, of course, the formulation information that were provided that was used in the demonstration test. But since we were doing the assessment not for the C8 itself, but based on the presence of these monomers or degradation products, we had to assume at which proportions they were present, and for this we took the information on the concentration of the C8 or C6 in the formulation, plus information on reported levels of monomers or degradation products in this for this type of polymers. So this led to this 0.6% that was used in the assessment. For PDMS and the dendrimer, we used the information of the safety data sheet. So if you look at the hazard class column, you see these letters are associated to a hazard class. The hazard classes in Stoffe Manager range from A to E, and being E the most hazardous level. In exception of the eye damage, where B is the lowest band, actually. For the exposure classes, they range from 1 to 4, being 4 the highest exposure band. And then the combination of these bands lead to the ranking of the risk classes. And you can see that in all cases there was the risk class was low, except for inhalation and systemic exposure after skin exposure that was moderate for the C8 substance, and then also for skin contact for the dendrimer there was a moderate risk. This table summarizes the comparative assessment, and you see each of the alternatives in which hazard and exposure band they sit, and also by the colors you can see the risk band that corresponds. And this is another table, in this case for the skin, for the dermal exposure. The first one was for inhalation, and this is for dermal exposure. So in both cases, the C8 points out as more as holding a more risk scenario, and this is mainly due to the fact that it's a CMR substance. Then the main conclusions were that the textile finishing industry has limited information to take into consideration safety aspects associated to the DWOR active substances in their commercial formulations. And in most cases, the identity of the active ingredients and their concentrations is not disclosed. Most of the DWOR are based on polymers, which are considered not hazardous, generally considered as non-hazardous due to their lack of bioavailability, and consequently there is no legal obligation to include them in the safety data sheet of the commercial products, although we know that their precursors and degradation products could be hazardous, as in the case of C8. The concentration of these unreacted monomers in the commercial products should be reported, and also there should be information generated on the degradation of these DWOR active ingredients during the drying and curing steps after the padding impregnation treatment, and then also on the hazard properties of such degradation products. Since this information was not available, we had to take a large number of assumptions that are affecting this risk assessment process, so we need to acknowledge a large uncertainty on the results of this analysis. And this is all for this part.
Thank you very much, Gemma, for the overview of the assessment for occupational risk. Let's move right along into the project recommendations based on the outputs. So Gemma will start this presentation, and then we'll turn it over to Marc Torrentellé. So just if I can ask you to keep it concise, that will leave us some more time for questions.
Yeah.
Okay.
So I'll continue with this, and I'll just focus my part on recommendations for the region axis. As I just said, most of the words evaluated were polymers, and I already highlighted the challenges that these represent. So this region CLP legislations include specific provisions and requirements for polymers, but they are exempt from registration and evaluation under REACH regulation. This is under revision. This is already considered in Article 138 of REACH, the possibility to revise this situation, and even now under CLP there is a requirement to notify a polymer if it fulfills the criteria for classification. But based on this situation and also the challenges that we face in the MIDWOR project, we undertook this review of documents that could be useful to identify critical factors determining potential hazards of polymers, and also different regulatory approaches that exist on how to assess risk by polymers in different countries, and also which data requirements they require under different jurisdictions, in order to recommend how to tackle polymers and identify need for to face additional regulatory requirements. So the proposal is that the main factors determining polymer hazards should be reported and used to discriminate between polymers with potential hazard concern and polymers with low concern. Such critical factors are information and human health and environmental hazards of the polymers, if these could exist, otherwise average molecular weight and oligomer content, presence of functional reactive groups, and residual monomer content, impurities and degradation products. And with all this information, polymers could be classified either as polymers of hazard with potential hazard concern or polymers of low concern. This consideration of polymers of low concern is not new. The OECD has a definition since 2009 on what a polymer of low concern is, and those are deemed to have insignificant environmental and human health impacts, and therefore should have reduced regulatory requirements. So we endorse these recommendations, and our conclusions were that polymers should be registered under REACH, but that there should be exemptions of information requirements for low volume of manufactured imported polymers, also for polymers which are aimed at use for R&D purposes, and polymers of low concern. And I'll pass now the word to my colleague Marc.
I'm Marc. I'm going to continue with the policy recommendations. In MIDWOR, chemical substitution policies favoring the use of fluorine-free alternatives in textile finishing processes must be promoted at European level. However, these policies must take into account that there are some remaining critical uses for which there are no suitable alternatives available yet. So for these cases, derogations to C6 fluorinated products should be considered in those uses where oil repellency properties are required due to lack of alternatives. It's highly recommended to use only fluorinated products when absolutely needed due to performance requirements. Industries should be part of the process and should contribute to further define these critical uses. Some of these critical uses can be, for example, for protective clothing or automotive fabrics, upholstery fabrics, or other applications. Depending on the intended end use of the textile product, a fabric may require water repellency or oil repellency. And in some cases, not all performance attributes are necessary on a fabric. Research and development for alternatives is ongoing and needed to make certain that non-fluorinated chemistries can provide the desired fabric attributes as well as meet their defined performance requirements. And further performance tests should be conducted with different types of fabrics in order to assess the technical feasibility to apply different DEWOR products. More knowledge on hazards and environmental data of DEWOR products would be helpful to reduce data gaps and produce more effective policies dealing with DEWOR products. And for example, most of the safety data sheets consulted for the products selected in the project do not provide specific information about biodegradability or data about the bioaccumulation potential. So there is insufficient qualitative and quantitative public information also about the ingredients, as said before, Gemma, and only a few specific ingredients are stated, and for these limited data on health and environmental properties are available. In MIDWOR, we have also analyzed what's the influence of DEWOR products on textile products that wish to obtain the European eco-label. The European eco-label for textiles products is a voluntary scheme aiming at promoting the products with a lower environmental impact. And to obtain this eco-label, textile products must meet 28 different criteria affecting different production stages from spinning to finishing processes. This criteria is grouped into six categories: textile fibers, components and accessories, chemicals and processes, fitness for use, corporate social responsibility, and supporting information. And in two of these 6 groups, there are some criteria affecting the DEWOR products. In particular, there are 2 European eco-label criteria related to the information to be provided by the DEWOR suppliers, and that limits the use of certain chemicals. For example, criterion number 13 says that fluorinated water, stain and oil repellent treatments shall not be used, and that non-fluorinated treatments shall demonstrate that they are readily biodegradable or non-bioaccumulative. The final textile product shall contain neither substances included in the authorization list nor substances included in the candidate list of substances of very high concern. And regarding criterion number 14, there are more than 30 hazard classifications that shall not be used to obtain the European eco-label. Well, in this table, you can see the different DEWOR chemistries which were assessed in MIDWOR in order to determine whether they pass or fail the criteria number 13 and criteria number 14. For example, you can see that C8, C6 based products and perfluorosilicon products do not pass criteria number 13 because all of them are fluorinated substances. And concerning the fluorine-free alternatives, such as dendrimer, silicone, and paraffin, all of them meet the criteria number 13b, which is about substance of very high concern. But in the suppliers of these products didn't provide a specific information about biodegradability or their bioaccumulation potential. So it's worth mentioning that the last three products only provide water repellency properties, and therefore any of the substances assessed that provide oil repellency properties pass the European Ecolabel criteria. Yeah. As you can see, this refers to criteria number 25, which also affects DWOR products. And criteria number 25 requires that textile products guarantee a certain level of water and oil repellency, which is the text that is marked in red here in the slide. And based on the performance tests done within the project, it can be stated that textile products treated with fluorine-free water repellents may meet criterion 25, but it's not easy. In fact, from the 3 fluorine-free products applied in polyester fabrics, only the dendrimer has the potential to meet with water performance requirements established in criterion number 25. On the other hand, textile products treated with oil repellents are not suitable to obtain the European Ecolabel, since currently only fluorinated products meet with the durability criterion. And however, these products do not meet criterion number 13, which is about the substance of very high concern. And finally, in MIDWOR, we also have provided some recommendations for the future revision of the reference document on best available techniques for the textile sector. The BREFs are a series of documents that reflect an information exchange in the European Union carried out according to the Integrated Pollution Prevention and Control Directive, which was derogated later by the Industrial Emissions Directive. And since the current version of the BREF for the textile industry is from 2003, there is a need to update this document, and for this reason we provided some recommendations. Well, as you can see in the table, for example, we suggested in some chapters to make reference to some of the alternatives studied in the project, like for example, introduce the dendrimers in this important document. And also, as a future work, we suggest to make more performance tests with the paraffin and silicone products that we use it in the project, but also with other DWOR alternatives. And that's all. Thank you.
Thank you very much, Marc, and all the presenters for really providing a lot of information about the different aspects and outcomes of your project. The presenters provided also a link to the project website where you can obtain further information, as well as I'm sure they'd be willing to discuss with you as well. Since we're at the end of the hour, I'll just pause to thank very much all the presenters for their work. I think it's there's a lot of different considerations in terms of the life cycle assessment and the occupational assessment for the particular 6 substances, and then also a number of ideas for both follow-up work and some indication from this project about potential policy options that could help better regulate some of these substances. I wish everybody a good rest of the day. Thank you.